In the last few lessons, we've spent a good bit of time talking about whole numbers and how to add, subtract, multiply, and divide them. These topics are very important, so I hope that review was helpful to you. I also hope that you have a certain level of mastery of those subjects now as we move forward in this course. Working with whole numbers is a very important thing, but bottom line, life isn't just about whole numbers. We're often dealing with parts of whole numbers, needing to add 2/3 of a cup of water to a recipe, cutting a piece of board 5 3/4 inches long for a small construction project, or giving a small child 1/2 teaspoon of medicine. These are not whole number amounts, but they're what we call fractions. And over the next few lessons, we're going to learn lots of different facts about fractions, what they are, how to tell when two fractions are actually equal to the same amount, how to add, subtract, multiply, and divide two fractions. Now, I know the topic of fractions has been unenjoyable for some of you in the past. Don't worry, we're going to take this step by step, and I'm confident that you can master this very important material. So let's start with just some basic definitions and terminology. First, the word fraction comes from a Latin term which means to break, the same root word from which we get the word fracture in English, like when you break your arm or you break your leg. So the idea behind a fraction is that it represents a part of the whole or a portion of something. Another aspect of fractions is that they are typically numbers which are expressed as a ratio of two whole numbers, like 2/3, which we sometimes call 2/3, or 5/9, 5/9, or 15/4, which we call 15/4. And just a bit more terminology is very important for us. The two numbers which make up a fraction have very special names of their own. The top number is called the numerator, and the bottom number is called the denominator. In a nutshell, they represent two very distinct things. The denominator, which is the bottom number, often tells us how many parts we have broken up the whole into, while the numerator, or top number, tells us how many of those parts we actually have. As an example, we can think of a pizza as being cut into 8 equally sized slices. If we then take 3 pieces of pizza and put them on our plate, then we would say that we have 3/8 of the pizza on our plate. Understanding these different roles of the numerator and denominator will be extremely important, and I'm going to try to talk about numerous real-world examples in this lesson, just to help us fully understand the numerator and the denominator. Now, one of the most important but sometimes most confusing ideas related to fractions is that lots of different looking fractions can actually represent the same quantity. Let's look back at that pizza example I mentioned earlier to see what I'm talking about. Let's say you make a round pizza and you're a bit lazy about how many slices you cut. So you actually just make one big cut right through the middle, leaving yourself 2 large slices, one on top and one on the bottom of the pizza. If you then take one of those 2 slices, then you'll have taken 1/2 of the pizza, right? 1/2 of the pizza is on top and 1/2 of the pizza is on the bottom. Okay, the next day you start from scratch and you make another pizza, a new pizza. This time you're a little less lazy, and so you cut this pizza into 4 equally sized slices. You then take 2 of these 4 slices and put them on your plate so that you have 2 out of the 4 slices of the pizza, or 2/4 of the pizza if we think of it as a fraction. You have 2 out of the 4 possible slices. Remember, that's the role of the numerator, the 2 slices that you have, and the denominator, the 4 total slices. That's where we get the 2 and the 4. The numerator tells me how much I have. The denominator tells me how many total parts there are. But wait a minute, if you just look at the pizza for a moment, you realize that you still have 1/2 of this pizza again, because you've taken 2/4 of the slices. And that means, if you just want to think about the fractions for a second and put the pizza aside, 1/2 equals 2/4. Those two fractions are actually the same quantity. And that's pretty interesting because 1/2 and 2/4 look very different as fractions, but in fact, they're actually equivalent as fractions. And similarly, if you had cut the original pizza into, let's say, 8 equally sized slices, and you kept 4 of them for yourself, then you would again see that you have 1/2 of the pizza. So that means that the fraction 4 divided by 8, which is 4/8, is actually the same as 2/4, and that's exactly the same as 1/2. In fact, we could play this game forever. We could write down infinitely many different looking fractions, all of which mean the exact same thing as the fraction 1/2. We could have written down 3/6, 5/10, or 5/10, and so on. All of them would be equivalent to 1/2. Now, that leads us to an important definition. We're going to say that two fractions are equivalent to each other if they represent the same quantity, even if they look like very different fractions because their numerator or denominator look very different. So, for example, 1/2 is equivalent to 2/4, and 1/2 is equivalent to 4/8, and so on. We're going to use this word equivalent quite a bit in the next few lessons on fractions, so it would be wise for you to put it to memory. Now, this leads us to a few different questions that we really should ask and answer as we walk through this first lesson on fractions. First of all, is there a best way to represent fractions? In other words, is 1/2 better than 4/8 or 2/4? Well, you know, better might not be the right way to say it, but 1/2 definitely has a property that its equivalent counterparts don't have. And that is that 1/2 is written in what we call reduced terms. Now, that phrase, reduced terms, is going to come up over and over again, so let me explain to you what it means, because some of you are probably just not sure what I mean by that. Here's a definition that I want you to keep in mind. A fraction, let's say it's a over b, is written in reduced terms if the only divisor or factor that a and b share is the number 1. So, for example, 4/8, or 4 divided by 8, is not in reduced terms because both the 4 and the 8 share a common factor. In this case, a factor of 2, because 4 is evenly divisible by the 2, and 8 also is evenly divisible by 2. Okay. 2/4 is also not in reduced terms because the 2 and the 4 also have a common factor, again, a 2. And 3/6 is not in reduced terms because the 3 and the 6 both have a common factor of 3. So even though 4/8 and 2/4 and 3/6 are all equivalent to 1/2, it turns out that the only fraction in this family, which is in reduced terms, is the 1/2. Now that makes the 1/2 special in some sense. Better or best, I'm not really sure if that's the right language, but definitely it's the case that 1/2 is special because it's in reduced terms. Let me try to motivate it this way. You might say to me, who cares if a fraction is in reduced terms? Well, let me try to put it to you this way. Which one do you think is easier? Finding 1/2 of a pizza, which only has been cut into 2 huge pieces, you know, 1 piece on top and 1 piece on the bottom, so that you've really just cut right through the middle, and all you have to do is pick up 1 big slice? That's really what 1/2 means. Is that better? Or is it easier to cut a pizza into 100 tiny little slices and then pick up 50 of them? Well, guess what? 50 over 100 is actually equivalent to 1/2. And I'll show you a way to check that in just a minute. But wow, which one would you rather do? I don't want to have to cut a pizza into 100 equally sized slices and then pick up 50 of those little pieces in order to visualize 1/2. It would be the same thing, but it's much easier to just cut the pizza into 2 big slices and pick one of them up. That is an easier representation of 1/2 of the pizza, and that's one of the reasons that 1/2 is a better way of viewing the fraction than 50 over 100. Now, that's not an airtight argument for why fractions which are in reduced terms are the best ones, but believe me, we will most often want to get our fractions into reduced terms when we're finishing our work, and actually in the process of doing some of our adding, subtracting, multiplying, and dividing, we will also want to have our fractions into reduced terms as often as we can. Now, this raises several other questions that we need to think about in this lesson as we deal with our introduction to fractions. For example, how can I tell when 2 fractions are equivalent if the 2 fractions are a bit ugly? I mean, I've been dealing with things like 1/2 and 2/4 and 4/8 in this lesson up to this point. Those are kind of easy to see, but is it easy to tell whether 6 over 14 and 15 over 35 are equivalent? Well, not really at the beginning, but I would like to show you 2 different ways that you can check to see if these 2 fractions are equivalent. So let's talk about that for a few minutes. Let's see 2 different ways to check whether 2 fractions are equivalent. First, you could always take the 2 fractions that you have and just reduce both of them to their lowest terms if you like. It's that simple. If the 2 original fractions are equivalent to one another, then they must be equivalent to the same reduced fraction, or fraction that's in reduced terms. So let's try that in this example. Let's start with the fraction 6 over 14, and let's reduce it down to its equivalent fraction in reduced terms. Okay? That means that we need to start dividing out the common factors, the factors that 6 and 14 share. So, what factor do 6 and 14 both have in common? Well, they're both even, right? So they must both be divisible by 2. Let's divide a 2 out of the 6, and let's divide a 2 out of the 14. 6 divided by 2 just leaves me with a 3, and dividing out a 2 from the 14 leaves me a 7. So 6 over 14 is equivalent to 3 over 7. Now, is 3 over 7 in reduced terms? Yes, because the only divisors of 3 are 1 and 3 doesn't evenly divide the 7. So I can't reduce 3 over 7 any further. 6 over 14 reduces to 3 over 7, and I stop. Now, what about the 15 over the 35? That was the other fraction I was thinking about. Can I reduce that one? In fact, I can, but before I do, why don't I suggest you try reducing 15 over 35 yourself to see what you get when it's in reduced terms. Well, if you think about it for just a moment, you can see that 15 and 35 both have a 5 as a factor. And if you divide out a 5 from the 15, it gives you 3. 15 divided by 5 equals 3. And if you divide that same 5 out from the 35, you get 7, because 35 divided by 5 is 7. That means that when you start to reduce 15 over 35, it's equivalent to 3 over 7 as well. Now notice something. 6 over 14 reduced to 3 over 7, and 15 over 35 also reduced to 3 over 7. And since both of those fractions have the same reduced fraction, if you will, the 3 over 7, it means that 6 over 14 and 15 over 35 are equivalent to one another. And that's very nice. That gives us one way of checking whether 2 fractions are equivalent. But there's a second way to check whether 2 fractions are actually equivalent. And I like this second way because I think it takes less work. Well, it definitely takes less ingenuity because I don't have to worry about trying to reduce both of the fraction to their lowest terms possible. and thinking about all those common factors and so on. This is a nice way to just do the process, and it's a very basic technique. So let me explain it to you here. If two fractions, a over b and c over d, are actually equivalent to one another, then a times d has to equal b times c. Or in other words, the top part, or the numerator of the first fraction, times the bottom part, or the denominator of the second fraction, has to equal the denominator of the first fraction times the numerator of the second fraction. Some people like to call these the cross multiplication terms or the cross product terms. If they're equal, then the original two fractions are equivalent. And it's that simple. There's nothing else to do but to check these two products, these two multiplications for the fractions. So let me go back to the example we just finished and confirm again that 6 over 14 and 15 over 35 are equivalent using this new technique. Well, the first thing we do is multiply the 6, the numerator of the first fraction, with the 35, that's the denominator of the second fraction. Hey, we've done that kind of thing before. Just a few lessons ago, we multiplied things like 35 times 6. And here again, the mathematics is building on itself as we walk through this course. Now, if you think you can do it quickly here. What do you get when you multiply 35 times 6? Well, if you walk through it and do the long multiplication, you're going to get 210. And that's great. Now, let's do the same thing with the other numerator and denominator pair. Now I need to multiply the 15 with the 14. Again, this is a nice multiplication problem with two two-digit numbers. So feel free to pause the lesson again and check to see what you get when you compute 15 times 14. Well, what did you get? You should have gotten 210. And hey, that's exactly what we got when we multiplied 35 times 6 just a few moments ago. Both of these cross multiplications are giving me 210. What does that say? It says since we got the same number with both of those multiplications, we know that the fractions 6 over 14 and 15 over 35 are equivalent to one another. Now, let me repeat myself here. I like this technique because we did not have to reduce the two fractions that we started with in order to see if they were equivalent. We simply had to go through two multiplication problems in order to figure out the equivalence, and I think that's pretty nice. Now, I'd like to try one more example of this technique to see if two fractions are equivalent. So let's do this quickly. Determine whether 8 over 13 and 12 over 15 are equivalent to one another. Now here I'm going to use that second technique for checking their equivalence. So that means I'm going to multiply numerator of one fraction times denominator of the other fraction, and then do the same thing with the other numerator and denominator. So I need to find 8 times 15 and 12 times 13. Okay? And notice we're not multiplying a numerator with its own denominator. We have to multiply numerator of one fraction with denominator of another fraction and then do the other. Okay? Well, what do you get? Well, pause the lesson if you'd like, do those two multiplications and see what you have. 8 times 15 is the same as 15 times 8. If you do that multiplication, you get 120. And 12 times 13, which is the same as 13 times 12, gives you 156. Since 120 is not the same as 156, we know very quickly that 8 over 13 is not equivalent to 12 over 15. Now, you might say to me, well, that was useless because all we found was that the two things weren't equivalent. Well, that's not true. Actually, by doing that example, we've learned something. We now know that these two fractions are not equivalent, and that's something important to know. But we also know something more, which I'd like to tell you about now. Believe it or not, I now know which of those fractions, 8 over 13 and 12 over 15, is actually the larger of the two. Remember, they're not equivalent. That means one of them is bigger and one of them is smaller than the other. So this technique will now actually tell me the relative sizes of the two fractions. Let me state the main rule here, and then we'll go back to the calculations with those two fractions to tell which one is larger. Here's the main rule. Start with A over B and C over D. Calculate those two products, A times D and B times C. That's the part we've been doing. If the amount A times D is larger than the amount B times C, then the fraction A over B is the larger fraction. If, on the other hand, the amount B times C is the larger of the two cross products, then the C over D is actually the larger of the two fractions. Now you might say to me, oh my word, I'm so confused. Well, don't be. Here's a verbal way to say the rule I just mentioned. Multiply each numerator with the other fraction's denominator. Find the amount which is larger and identify the numerator that was used to get that amount. Then the fraction with that numerator is the larger fraction. The key here is which numerator gave you the larger multiplied amount. So let's go back to 8 over 13 and 12 over 15. We saw that 8 times 15 equals 120, and 12 times 13 equals 156. The 156 is larger than 120, so the 12 times 13 is the larger of the two cross products. The numerator used there is the 12 from the 12 over 15. And that means that 12 over 15 is a larger amount than 8 over 13. And that's a really nice result. Now, in a few lessons, we're going to talk about converting fractions to decimal numbers, and that'll give us another way to see which fraction is bigger. But until then, I really like this cross-multiplying trick. So let's look at one more example of this just to make sure we have it down. I'd like you to think about it first before we work through the details. So on your own, determine which of the following two fractions is larger, 7 over 8 or 10 over 12. Okay, we're just going to do these two cross multiplications and we're going to find the larger of the two amounts. So as I go through that, I see that I need to do 7 times 12 and 10 times 8. Well, 7 times 12 equals 84 and 10 times 8 equals 80. Now those two numbers are close, but 84 is bigger than the 80. And so that means I need to look at the 84, which is the 7 times the 12. Which one has the numerator there? Well, it's the 7. That's the part of 7 times 12 which includes a numerator. And that means that the fraction with 7 as a numerator is larger. And therefore, 7 over 8 is actually larger than 10 over 12. It's that simple. Okay, I'd like to shift gears now once more as we think about fractions in general. I've already talked a bit about reducing fractions which are not already in reduced terms, or what some folks sometimes call lowest terms. We've talked about that for a while. To be honest, reducing fractions just takes some practice in trying to identify or spot what some of those common factors are between the numerator and the denominator. Bottom line, it just takes practice. So I encourage you to work through several examples of reducing fractions. This is also going to come in handy in later lessons when we start combining fractions with addition, subtraction, and so on. So for now, let's just do one more problem with reducing fractions right here, and then we'll move on to a few more topics. Let's reduce the fraction 90 over 450 into reduced terms, or lowest terms. If you think you can do this one on your own, give it a try. All right. The key here is to start looking for common factors in the numerator and the denominator and to divide them out of both of the numbers. I should point out that this process can take very different tracks for different people. In this case, for example, I see that a 5 and a 2 can be divided out of both the numerator and the denominator. It's okay to divide out the 5s first and then the 2s. It's also perfectly fine to divide out the 2s first and then the 5s. In fact, it would also be fine just to divide a 10 from both top and bottom, from both the numerator and denominator. All of these approaches would be fine, even though they seem very, very different. The key is this: no matter what path you take to dividing out all of the common factors, whatever fraction you end up with needs to be the same. and there's only one fraction, which is equivalent to 90 over 450, which is in reduced terms. So it's not the path we take, it's whatever we end up with at the end, which is really the important fact. So let me start here by dividing out the 2 from both the numerator and denominator. I have that choice. Feel free to pause the lesson here and compute 90 divided by 2 and 450 divided by 2 using long division. Now, once you've divided out those 2's, you should find then that 90 over 450 is equivalent to 45 over 225 after you completed those long divisions. The 45 is coming from 90 divided by 2. The 225 is coming from 450 divided by 2. Excellent. But we have to keep going because our fraction now, 45 divided by 225, is not in lowest terms. Let's now divide out that 5 from both the numerator and the denominator. When you do that, you should have 9 divided by 45. Now what? Are we done? Well, no. It's pretty easy to see that 9 has a divisor of 3 in it, and it turns out that 3 is also a divisor of 45. So now we need to divide a 3 from both the numerator and the denominator. When I do that, it leaves me with 3 on top, because 3 times 3 is 9, and it leaves me a 15 on the bottom, because 15 times 3 is 45. And wait a minute, there's still a 3 in both the 3 and the 15 in the numerator and denominator. I have to do the process again. When I divide those 3's out, I will have 1 on top and 5 on the bottom. And there's nothing more I can do to reduce that fraction. So that means that 90 over 450 is actually equivalent just to the small fraction 1 over 5. But how would I check that? I mean, you may feel a little uncomfortable with that answer. Well, just do the cross multiplication trick. You have 90 over 450 and 1 over 5. If they're really equivalent, then those cross multiplication amounts have to be the same. Well, let's check. 90 times 5 is one of those cross multiplications, and that's 450. You can do that just like we've done in previous lessons. And then the 1 times 450, well, that's just 450. Anytime you multiply by 1, you just get the other number back. So 1 times 450 is 450. Those two amounts are the same. And that means that since the cross multiplication amounts were the same, the two fractions, 90 over 450 and 1 over 5, are actually equivalent fractions. Now, as we close out the lesson today, I want to mention 2 more vocabulary terms which are related to fractions. They're called improper fractions and mixed numbers. An improper fraction is a fraction whose numerator is actually larger than the denominator. So fractions like 11 over 5, 3 over 2, and 200 over 130 are all improper fractions. I'm honestly not sure why these are called improper, but it almost sounds like there's something wrong. Well, you know, like when someone tells you your behavior at the dinner table is improper, it usually means you're doing something that you shouldn't. Well, here it's not that much of a problem to have improper fractions. However, there's a way to rewrite improper fractions so that the numerators are smaller than the denominators, and these are called mixed numbers. A mixed number is a whole number that is combined with a fraction. So for example, 2 1/3 is a mixed number, and 5 1/2 is a mixed number, and so is 10 2/3. These are very common numbers if you think about it. When you look at a sheet of 8.5 inch by 11 inch paper, the 8 1/2 is a mixed number. And how many times do recipes say to add something like 3.5 cups of flour to the mix? So as we close, let's just show how you can work between improper fractions and mixed numbers in the following way. Let's convert a number like 25 over 4 to a mixed number. Well, here's the basic idea. How many times does 4 go into 25? Or, if I said it a bit differently, how many 4's can you subtract out of 25? Well, the answer is 6, because 6 times 4 equals 24, which is less than 25, but 7 times 4 equals 28, which is larger than 25. So we can actually pull out a 6 from the 25 over 4, and how much of the numerator is left after taking out that 6? which is like taking 24 out of 25? Well, just 1. So 25 over 4, which is an improper fraction, is the same as 6 1/4 as a mixed number. And there you have it. Now, I'd like to close this lesson by doing one more conversion of an improper fraction to a mixed number. The idea is the same as it was before. I need to ask this question. How many times does 3 go into 47? Well, that's just a long division problem. So feel free to pause the lesson here to complete that long division. Now, what did you get? Well, the answer is 15 with a remainder of 2. And guess what? That tells you all you need to know. 47 over 3 is the same as the mixed number 15 2/3. The 15 was the quotient from that long division problem, and the 2 was that remainder at the end. So I know that the improper fraction 47 over 3 is the same as the mixed number 15 2/3. Now, as we close this lesson, I'd like to make sure that you feel comfortable with these fractions. Lots of terminology that we've walked through today, including these ideas of mixed numbers and improper fractions, but even things like numerator and denominator and equivalent fractions. Next time, we're going to start working with adding, subtracting fractions. And it's going to be very important that we understand what we've done today in order to work on the material in that next lesson.